Okay, yeah, please, Chi, whenever you're ready. Yeah. Okay, please, Chi, whenever you're ready.
Okay. Okay. Thank you very much for coming. I will talk about this this paper, Taylor structures for holomorphic submersions. Yeah. So the question, I guess, is very natural. That is, if we have a holomorphic submersion, so you have a vibration, holomorphic vibration with smooth fibers. So pi is holomorphic. Uh, and it's submerged at any point. Then we want to give a criterion for the total space X to be Kähler. So the question is, sorry, let me. Yeah, well, we want to, the question is, one is X Kähler. Of course, there are some necessary conditions. First, condition one is that each fiber must be Kähler, right? And actually more there's a slightly strong there's a stronger necessary condition, that is there exists cohomology class on the total space such that the restriction of this cohomology class to each fiber, I will denote this fiber as XB, is a Kähler class. On this fiber. In particular, each fiber is a Kähler manifold. That's first condition. The second condition is that actually B is also Kähler. This is maybe less obvious, but if let's say if Q is Kähler, is a Kähler form, on the total space, then one can get a Kähler form on B just by integrating this Q to let's say m plus 1, and you get close the this is a Kähler form on B. Where let me denote m to be the dimension of the fiber, and n is the dimension of X. Okay, so n minus m is the dimension of the base. Right, so so the main result is that these two conditions are also sufficient. So in this Kähler metric.
I guess you mean integration along the fibers of Q to the n plus 1, right? Not along the base.
Oh yeah, sorry. Yeah, integration along the fiber. Exactly. Thank you.
Yeah, thanks.
Yeah, please stop me if you find anything not clear to you. So there exists a Kähler structure on X if and only for both condition 1 and the condition 2 holds. So this does not seem to be very surprising, but there's something I find interesting. For example, actually, this immediately answer a question of Harvey and Lawson. Let's check. Harvey. Lawson. That is when the fiber has dimension 1. It's a Riemann surface. Of course, everything here is compact. Okay, I assume that these are compact manifolds, complex manifolds. Both X and P. Assume the dimension of the fiber is 1, complex dimension. And assume B is the base is scalar, any dimension. Then the total space is scalar if and only if the homology class of the fiber, which is independent of the base point, is not zero. Yeah, so it's just a easy exercise to derive this corollary, basically because you basically, if it's not, you look at this maybe short previous, you look at this restriction map from this H2 X R to H2 X E R. So this condition is equivalent to saying that this is surjective. Of course, when the fiber has complex dimension 1, this is just isomorphic to R. So it's basically saying that because here then you have you have this natural class, that is the basically a canonical class of the Riemann surface, right? So this just the canonical class that represents the orientation of the volume form, representing this H2 of the fiber. So this not zero is equal same thing as is surjective, and then this will imply the condition 1 holds. And then you just apply this theorem. So it's not a trivial result, as it may seem first to be.
Sorry, Chi, are you assuming the fibers are smooth?
Yeah. I assume everything's smooth. Yeah, smooth.
Okay.
Yeah. Of course, the probably natural question is to weaken these assumptions. Okay. So in some sense, I guess this theorem can be seen as a generalization of this corollary to the case of higher dimension fibers. Okay. By the way, Jeff, how much time do I have?
Usually, well, I mean, in principle, we schedule it for like as much as 2 hours, but usually, basically, people just sort of talk for like an hour and a bit more, maybe. Like you can just take your time and.
Okay. Okay.
In any case, yeah, like basically
Yeah.
whatever you want, I guess.
Okay. Sorry. Okay. Yeah. Okay, and then let me now introduce a different equivalent version to this theorem, which may seem more technical. To do that, I have to recall something called the Ricci spectral sequence. This is a spectral sequence which allows us to calculate the cohomology of the total space. So it's a spectral sequence. With the Euro notation, it's some vector spaces and maps between these vector spaces, such that yes, the next page is given by the kernel of this DR, and this converges in some sense to the cohomology space, cohomology of the total space. And the important vector space for us is the vector space appearing in the second page. Actually, we also look at the first page, but let's do the second page in order to state the theorem. This is given by this one. This is the so-called local system. Roughly speaking, somehow you attach some fiber vector bundle such that each fiber is this HQ of XB, let's say with R coefficient. And of course, if you have a different fiber, then you have a isomorphic vector spaces because they are diffeomorphic. So, and the point is that in this case, actually there's a natural connection, which is called the Gauss-Manin connection, which allows us to parallelly translate one cohomology class to another. So this is horizontal. So there's a natural horizontal direction, and this corresponds to its so-called Gauss-Manin connection, which is intrinsically attached to this local system. Next. As I said, it's obtained by just translating the homology class from one fiber to another. So because you can always, if you think of cohomology, a cohomology class as represented by some manifold, then you can move this sum manifold to a nearby fiber to a different fiber, and then you can show that this this gives you a flat, actually it's a flat connection. Curvature is 0. But the one thing that's more interesting is that you see, in this case, you can, whenever you have a flat connection, you can look at the translation, parallel translation after you go around the loop, right? So you have a loop, then you go around the loop, and you go back. Of course, if it's if the loop is homotopic to 0, then you get the same element. But if you have a non-trivial topology, then you go around this loop, then you may end up with some different element. And this means that in general there's some monodromy, non-trivial monodromy. So it's you in general you have like monodromy acting on the fiber. Sometimes I will denote this fiber just as B at point B. So you have a natural monodromy group. Okay. So now this D2, this and the second page, this D2, with the in particular maps H0 B R2 I star R to H2 B R1 star, something like this. Yeah, if you check this subscript, then you see something like this. Yeah, so this is a D2. Okay, so now I can state another theorem. Okay, maybe before I say this theorem, then let me recall a theorem that is an important theorem in Taylor geometry. It's proved by Blanchard. Usually attributed Blanchard and Berlin. So this theorem says that if X is scalar at in the box setting, then actually the respectral sequence degenerates at E2, which means that actually all these map, these dr is equal to 0 when r is bigger than equal to 2. Yeah, so this is the theorem proved earlier. So now I can state another version of this previous theorem. Okay, so this can be thought of as like a converse to this theorem. To this theorem. So but I have to again basically I want to split this condition 1 into two different conditions. Remember the condition 1 originally says that there exists a cohomology class on the total space such that the restriction is a Taylor class. I can split it in two conditions. The first condition is that there exists let's say Q. That is H0 B R2 I star R. Remember, this basically means that you have a flat vector bundle such that each fiber is H2X. So assume that there exists a global section of this flat bundle, which means that it's invariant under parallel translation, such that restricts to the Taylor class. On each fiber. And condition 1b says that this D2, when you X on Q is equal to 0. Remember, we have this D2 from H0 BR2. Yeah, I guess it's written here. So you have a Q here. You can map it to this D2. So I want Q to be in the kernel of this D2. And then condition 2 is still the same, the B is scalar. And then this theorem says that this hold if and only if x is k. Yeah. Basically, I want to say that these two together would imply imply condition 1, which means that you can find a Q that is actually in H2 of the total space, such that the restriction to each fiber is clear. It's easy to go from this condition 1 to condition 1A and condition 1B. So, but the other direction uses these scalar conditions on the fibers, and yeah, so you use this scalar condition on the fiber, and we will see it in the proof. Is the statement clear?
Yep. Yeah.
Okay. Let me just give you a proof in the case we have a stronger assumption, and you will see what's the main difficulty here. So the proof one for the case you can choose Q. Remember, we assume that there exists a homology class H2XR. Let's assume Q is represented by a closed 1-1 form. Okay. Of course, in the original theorem, we don't assume this. We just assume it's represented by 2 form. Because by Drum, let's say, if you look at the Drum homology, then we only require Q to be represented by 2 form, closed 2 form. But let's make this a stronger assumption, then we will immediately prove this result, because then you can restrict right by 1-1 form that's still denoted by Q. And then you can restrict this to each fiber, and you know it's represented by sorry, it is a Kähler class, right? So it's a Kähler class. So you can choose, let's say, choose a Kähler form on the fiber, and by this DD bar lemma, then you can find this function, let's say, psi B, and you can normalize, for example, to make it to have value 0 average. Right. And then somehow you can also assume that psi B, let me see how do I say this. Yeah, you can also actually construct you can assume by using the first assumption, by the first assumption, yeah, you can by this condition 1A, you can construct a family of Kähler forms that depend smoothly on B, right? Just by using some partition unity argument. And then this would imply that this psi B actually is also smooth with respect to. Which give us a globally defined smooth function on X. You just put them together. And then you define, let's say, Q minus root minus d by psi. We call this Q prime. Then this, when you restrict to each fiber, then it becomes it just becomes omega B. It's okay. So in other words, we find closed one-one form whose restriction on each fiber is Kähler. And then you know that you have a Kähler metric on the base, so you can multiply this by a very large number and you add to this Q prime, and this would become a Kähler for K sufficient large. Because basically Q prime is positive in the vertical direction, and this is positive on the horizontal direction. So if you add sufficient large, of course, this is the pullback of the Kähler metric on the base. Then this would become a Kähler metric for K sufficient large. So that proves this theorem. But you see here, we assume that Q is already a one-one form. So then this would allow us to construct a one-one form that is closed, and also its restriction on each fiber is Kähler. So this breaks down if Q is just a two form, closed two form. Then this Q, then this construction, the same expression as above is would be something called a Hermitian symplectic form, which means that let's say if we call this to be, let's say, chi, which means that this is a symplectic form, so it's non-degenerate, and d chi is equal to 0. And also that's one part. There's a complex manifold you can decompose into one part and 2, 0, 0, 2 part. This is positive, definite. But the problem is that you may have a extra 2, 0 and 0, 2, 4. Okay, so this structure was studied by previously by Tianjun Li and Wei Zhang, and also by Spitz and Tian. Actually, I think they somehow propose this problem whether there exists a complex manifold that admits just Hermitian symplectic structure but not a Kähler structure. So the question is there exists a complex manifold that has Hermitian symplectic structure but not a Kähler structure. This question, I think, is still open, but there are some results, and most results are negative results, which means we don't have any example. So this result we are talking about actually give another negative result, which means that there is no such example for holomorphic submersions. Right. So if you have a holomorphic submersion structure on convex manifold, then this X cannot be only Hermitian sympathetic but not Kähler. So which means that if you have such a holomorphic submersion, then actually if you have a Hermitian sympathetic structure, that would imply that you have a Kähler structure. Right. So this is not a direct corollary, but there's some probably I should write it as a proposition because there's some other ingredients besides this previous theorem.
Sorry,
Yeah.
For this last result you stated, do you assume that your Hermitian symplectic structure is of this form of something pulled back from the base plus?
No.
Or this is for arbitrary?
Oh, actually, let me see. Sorry. Actually, I have to be a little bit careful. I didn't put this such a stronger result. Actually, the answer is no. I don't assume any form of this Hermitian symplectic structure is of this form. Yeah. So because you see the existence of a Kähler structure does not assume anything about we'll be able to construct some Kähler metric on the total space, but we will not do it in this way directly. I mean, this way does not work. Yeah. So we'll do it in a more complicated way. Yeah. Actually, I think that I cannot prove this good statement. I can only prove that if this holomorphic submersion satisfies some condition. If I satisfies let's say one of the following. Oh, actually, let me just state because I want to make it clear what's the relation between. Actually, I can show that the Hermitian symplectic structure implies the second condition. Sorry, the condition 1b on X. So in other words, if you can show condition 1a also holds, then sorry, I guess I also need to assume the fiber and the base are Kähler. Right. So the idea is that we want to see if there's a possibility to construct such an example just by using holomorphic submersions, where the fibers and the base are already Kähler. Is it possible to construct a non-Kähler example? So the answer is it is not clear yet, but at least we can show the condition 1b holds. In particular, this implies, for example, if let's say as a consequence if in particular, for example, if the holomorphic submersion is isotrivial, then actually one can show that in this case, indeed, so there's no such example. So that means access to it. Because in that case, actually, you can show that the condition 1A is also true. That's one of the conditions you can use. The other condition is that if you know that the fibers are torized, then it's also true that so that's the first condition. And you can also add another condition. Is XB are tolerant, but maybe with a different complex structure. So if one of the following condition holds.
Isotrivial mean that all the fibers are biholomorphic, or?
Yeah, exactly. So the fibers are biholomorphic. So different. Yeah, for example, I guess previously there are some negative results which says that if you have a new manifold with a left invariant complex structure, then formation symmetrically implies scalar. And for some of these left invariant new manifolds, I guess there's some torus vibrations. And for those examples, you can also use this result to show that there exists no counterexample to, no such examples. So it recovers part of that result, but this is the first condition allows any fiber. So as long as it's isotrivial, like fibers are biholomorphic to each other, then this is always true. You can also add some other condition. For example, you can assume, let's say, the monodromy group is actually trivial. Remember, we have this monodromy action, which we explained earlier. Monodromy action. Monodromy action is by this fundamental group of the base. It's trivial. Then it also implies this same conclusion. So basically, you can show that these conditions, any one of these conditions actually implies the condition, not together. Any one of them would imply the condition 1A. And then you can apply this main theorem to get this position. Okay, that's the relation between this result and the earlier first result. Okay, yeah, I think that's one application of this existence criteria. Actually, I forgot to make another remark. That is this existence criterion for Kähler structures. This theorem, main theorem, generalizes a criterion of Blanch. He considered a case very special. He considered actually the case when you have a holomorphic, you have isotrivial holomorphic submersion, isotrivial case. And also, I think he also assumed this action is trivial. Yeah, he assumed very strong condition, and then he derived a criteria for X to be catered. So this main theorem is, you can use either of these theorems, the more technical version or the original version. They generalize this criteria of Blanchard to the more general situation when you allow any homomorphic submersion with the when the fibers change the convex structure, and also we don't add any assumption on the homomorphic on the monodromy action. Of course, the question is whether you can still weaken assumption. For example, if you can allow try to allow singularities. Yeah, that's a natural question to ask. That would probably lead to some more results concerning the mission sympathetic structure. Okay, so any question?
So yeah, maybe just so I understand, you don't sort of completely rule out holomorphic submersions. I mean, it's with these conditions 1, 2, or 3, I guess.
Yeah.
Okay.
Yeah, because I can only show the condition 1B holds, but I don't know if you can, because the condition 1A said that you can find Q, that is H2, actually, E, R2, I star, R, such that you restrict this to each fiber is tailored. If you just have a Hermitian sympathetic structure, you only know the restriction is also Hermitian sympathetic. So then I don't know how to find such a Q.
Can you recall in the proof you gave for the 1-1 case?
Yeah.
You use condition 1A to show that there exists this family of Keller forms which depends smoothly on B. Can you say something about how did you use condition 1A for proving that thing? Is this tautological or?
Yeah. So okay, good. Yeah, actually we will need this in our first step construction. Yeah. So thank you for asking. Yeah. Condition 1A, which says that there exists a Q in which 0 B R 2 R such that Q restrict to each fiber is K. Yeah. Right. So let me just try to see if I can explain. So you pick any point B. You pick let's say neighborhood. You look at this X B, and now you know that this is scalar, right? So we assume this is scalar. Just the restriction here, and then you look at nearby fiber. There's a result by Kodara Spencer about the stability of Keller structures. So you know that for any, let's say, B prime in a small neighborhood, then actually you also have a Keller structure. Actually, you can construct this Kähler form to deform smoothly. So you can find smooth varying Kähler forms as d prime varies in U, right? And then of course, this may not represent the restriction of Q to B prime, but then you can find let's say harmonic representative. Let's call this omega at B prime. Or maybe let's just Q B of this Q. So basically, we want to first perturb the Kähler form on one fiber to a nearby fiber, right? So with respect to this Kähler metric, because when you have a Kähler metric, you can have the you have Hodge theory, right? So you can look at the harmonic forms. So then this also is a smooth family of Kähler forms, right? Because when you it's a Kähler form when d prime is equal to b, then you just get this Q, which you choose to be some, if you choose some Kähler metric. Right? So near this point, you can find a family of smooth family of Kähler forms, but then you can just cover this compact manifold. Then you do the partition of unity. Let's say you call this to be Q, right? So you get a you get a 1-1 form, smooth varying 1-1 form. You call this, let's say, QU, and then you can just do this partition of unity. Then this will give you a 1-1 form. Let's call this Q minus such a Q. I think I denoted by Q. Yeah, just find this Q. Yeah, it's a 1-1 form. Such as the Q restricted to each fiber is Kähler. Yeah. It's just a partition unity argument, and together with this stability of Kähler structures. Okay.
Okay, so the partition of unity is just on the base, right? It's not...
Yeah. So yeah. So okay.
Okay, thanks.
Yeah. Yeah, pullback. Okay, so this is how we can actually achieve the first step of construction. Okay. If no other question, then let me just move on to explain the proof of this main theorem. Basically, we want to right. So you see, we have seen that by this condition, we actually construct a smooth 1-1 form on the total space such that its restriction on each fiber is a Kähler metric. But the problem is that it's not a closed 1-1 form. So our next goal is to make it closed. Yeah. So, and to do that, we have to use the second condition. Okay, so let's see how to modify this Q. Yeah, that's the first step actually. This is the first step of construction of the Taylor metric. So we get this Q from a form such that on each fiber is K. So the problem is that in general DQ is not zero. So it's not a Taylor metric on total space. So then we have to modify it. The idea now is to modify it step by step. So to do that, we introduce filtration. We introduce a filtration. On the E3. E3 is the space of differential forms of degree 3. Actually, let's do the for general Q, because probably at some point we need degree Q, a degree Q differential form. What is it? This is the differential form that locally, right? So locally you can write. Right. So locally you can write a differential form on the total space in the following way. Eta I K du I stretch dy. Okay. So here U is coordinates on the base, and this is the coordinates on the fiber. In other words, this pi is mapped right U y to U. This I is a multi-index because we want the I plus k to be equal to q. So dui is just du I1 wedge di, and the dyk is just dy j1 wedge d y j k. Right, and we want the number of base variables to be at least p. Actually, let me use R because this is related to this Lorentz spectral sequence. Yeah. Okay. What we want to do is we want to modify Q by let's say Q minus chi to find some chi such that yeah, just modify Q such that it satisfies dq is in FR3. Remember, Q is a 2 form, so dq is a 3 form. For R equals 1, 2, 3, and 4. Okay, so we do this gradually. So we first achieve this one r equals 1, and then r equals 2, r equals 3, and 4. The point is that you can see that f4 e3 is 0, right? Because you only have in this case you only have 3 variables. So this means that the variable on the base that there are 4 variables on base. That's empty. So an empty set. So this is so in other words, you have this decreasing filtration. I mean, you look at this, then it seems to be increasing filtration, but it's decreasing with respect to this R. Right. So now where are we? So actually, you will see immediately that this dq is here. This is because q, when you restrict to the on the so dq, when you restrict to each fiber, it's 0. Of course, this is same as dq restricted to xp. Pull back this stereo derivative. So in other words, if you look at this 3 form, if you restrict to each fiber, it's 0, which means that you have at least one base variable. Because if you have no base variable, then its restriction is not 0 if eta is not 0. So if you just have like eta k dy k, but no du variable, then its restriction is not 0. If you assume eta is not, but anyway, yeah. So this is already achieved. So we are already here. The goal is now to gradually make dq in this smaller into this smaller subspaces until it hits 0. Then we get rid of all the dq term, and then we get 0. Okay, that's the goal. So we want to modify this step by step. So in other words, r equals 1 case is already done. So we then move on to r equals 2 case. So in other words, we want to say that okay, now dq is in general has the shape let's say d. Okay, so for from now on, let me introduce this complex variable. So let's choose w to be the holomorphic coordinate on B, and the Z are holomorphic coordinates on the fiber. Okay. This means that this pi locally is given by pi wz is mapped to w, where w is w1 all the way to wm, and z is let's say z1 all the way to zd. D is the dimension of the fiber. Okay. So in general, what we can do now is this is equal to dw alpha yeah, wedge some let's say eta alpha bar, but not alpha bar, just eta alpha plus dw alpha bar wedge, and plus some term in the f2. Right, because as we said, so it's already landing landing F1. So this part is in F1. Okay, then we want to modify this Q. How do we modify this Q? The point now is that this eta alpha actually are closed. That is because you see this is a derivative, right? It's still a derivative. So you can show that eta alpha is actually closed. Okay, you can show that the eta alpha actually is not just closed, it's actually exact. Which allows us to write eta alpha as something like right. So here we have to be careful of the type. So Q is 1, 1 form, right? So this dq is 2, 1 plus 1, 2. So this is actually 1, 1. Yeah, because this is a this is a 1, 1 form. So if it's exact, actually we know that you can write this as let's see. Sorry, I guess there's some. Okay, I guess in general this is 1, 1 and the plus 0, 2. Yeah, because you see this is you take out the 1 from here, you get a 1, 1, and you take out the 1 here, you get a 0, 2. So that's why in general this is a 1, 1 plus 0, 2 term, 2, 2 form. But the point is that it's exact, and then this allows us to actually find eta alpha, write eta alpha as dh alpha. Okay, so this expression is local, right? So this is a local expression. So this h alpha, you can show that you can choose it to be 0, 1. Yeah, that's where this kind of DD-bar lemma plays a role. The Euro DD-bar lemma says that if you have a exact PQ form, then you can write it as DD-bar of some P minus 1, Q minus 1 form. There's a modification of this, which says that if you have a, let's say, P plus 1 Q, right? So if you have a exact form that has two parts, then that you can write it actually as some D of PQ form. Yeah. So that's the slight variation of DD-bar lemma. This was first, I guess, at least appeared in Blanchard's paper. So I should say that this idea of modifying Q step by step comes from this paper, but his paper only deal with a very special case. So so this step 2 actually is the same as in this paper. So you can find this H alpha 0, 1 form, and then you can write this chi as dw alpha, which okay, let me use bar to denote it's a 0, 1 form, plus dw alpha bar, which h alpha. You look at this form. Of course, this is a local one because everything depends on the holomorphic coordinates. But then you can construct the global one by again doing this partition unity. And then you can replace this q by q minus chi. And then you can check that indeed, in this case, dq minus chi. So basically allows you to cancel this term, right? Cancel this first part. And then you get some extra parts. But the point is that, remember this rho alpha, rho k is a partition on the base. So when you take the d of chi, right? When you take d of chi, then you see that because you already have one base variable, and you take a d again, then you hit this rho k, then you increase one base variable, so you are landed in the you have two base variables. You have two base variables. So this means that this actually is in F2 E3. Right. So in this way we can achieve the R equals 2 case.
And sorry, Chi.
Yeah.
I guess you're not really changing the like induced like the restriction of Q to the fiber, is that right? So it stays scalar every time.
Yes, yes.
On the fiber.
Yeah. Because when I restrict to each fiber, this term vanished. Yeah. Because W becomes constant and it vanishes. Right, exactly. Okay, so that's the second step. I mean, when R equals 2, then we move on. Then we need to do R equals 3. This is more difficult, and this is where this proof differs from Blanchard's proof. And this is where we need to use this condition 2, right? So remember, we have assumed that d2 omega, actually q, what I wrote it as q, is equal to 0 in the H2 R1. So now we have to use this. Okay, how do we use this? So we need to use a result by Deligne. So the idea now is that you think of this Q. This Q, you can okay, so I want to first claim that this dq, right? Right, so you see that now dq is in, now let's replace q by this one. So now this dq is in F2 E3. Of course, its restriction on each fiber is exact, right? So locally you can write this as okay. Locally you can write this as dw alpha dw beta wedge some like p alpha beta plus dw alpha wedge dw beta wedge p alpha beta bar, and then you add this complex conjugate, and then you have F3. So, because you don't have any term involving just one dw, you have these two, have at least two variables. So and then you know that this p alpha beta actually at least closed. Okay, so Now this DQ, let me see how to say this. I want to write this DQ as okay. Yeah, I think okay, let me see what is Q. Q is I want what I really want. I want to write this D2Q as the same as capital D of some time. Okay, let me write down this and I try to explain what this means. Okay, so this DQ when you restrict this subindex just means that I think of this as two form on the base with the so this remember we have this V, right? So each fiber is H1 X E R. So this is a so-called local system. So it's a flat bundle, vector bundle. So this is the V1 value, the differential form, two form on the base. And this is defined just by looking at the cohomology class of this P alpha and P alpha beta bar. And you think of this as the base differential form. And with the values, you take the class, right? So this is basically it's represented by dw alpha, dw beta, wedge, the cohomology class, plus dw alpha, dw p alpha beta. Right. And the complex conjugate. Yeah. And somehow you throw away this part when you take because you only look at the degree 2 part. Yeah. Remember, we assume that this D2Q is equal to 0 in this cohomology. So that this identity is just basically a definition because there's a way to describe the Lorentz spectral sequence using this filtration, right? So this is basically in Griffith's Harris book. Actually, I think they explain this by using this differential form. So you can think of this as a definition. And then this one, so there exists some chi such that this D is this, remember, this is a flat bundle. So then you can have a, 20p actually. It's like the drum type of the theorem, which says that this cohomology class can be calculated as a drum cohomology, but then you have to use this Gauss-Money connection, right? So this H2 of B of V is exactly the kernel of D, mod out the image of D. So if this is 0 in this homology class, that means that it's exact with respect to this D. So you can write this as a D of something, right? Okay, so now remember we want to keep Q to be a 1-1 form, so we have to require this chi again to be 1-1 form. It's represented by 1 form, and this is guaranteed by some DD bar lemma with respect to this operator. So now we need to have some like a kind of a Hodge theory for this cohomology group, or maybe for this operator. And turns out there's a Hodge theory which is first pointed out by Dallin, that you can actually have some Hodge decomposition for this cohomology group, and the decomposition comes like in the classical case. It comes from the decomposition on the form level. So you can write this as P plus Q plus R. So basically, you have to combine the decomposition on the base plus T. Right, so we have to combine the decomposition on the base, because the base is a compact, is a Taylor manifold, and it's a complex manifold, so you can decompose according to the types. And then the other thing is that each fiber is Taylor, and so this cohomology group, when you compensify, after you compensify, also has a decomposition, Hodge decomposition. So then you can look at the combined mixed decomposition, and then you can talk about the type of this V1 valued form, right? So here you see this DQ of gain, it's 2, 1 plus 1, 2, right? Of course, this 2 may come from right. So you have to decompose into the base and the fiber. So this 2 may come from the base. It may come from the base and fiber, and it may come from the fiber. So that's why we need to combine this decomposition. But the point is that there exists a DD bar lemma, like I call it D prime, D double prime lemma, because you can decompose this D also into the D prime plus D double prime, because you can like in the classical case, you can decompose this Gauss-Money connection into the D prime, D double prime, and then this allows us to choose this chi to be a 1-1 type. It's represented by a 1-1 form. On X. Yeah. Here is one also need to use some kind of partition of unity, put back something from the base and do something similar to what we did here. Yeah. And this would, yeah.
It's, I mean, so this D prime, D double prime lemma, this is some result specifically in the context of submersions, I guess. I mean, it's for when you have this Gauss-Manin connection.
Yeah. So this is actually a theory called the variational Hodge structures. Yeah. So it's a very special situation, but on the other hand, it's a very it's a bigger subject, like the study of variational Hodge structures. So it turns out this D prime, D double prime is not the obvious one. So somehow, for example, this D prime itself actually maps E P Q H E P R. Yeah, let me just roughly write down what it looks like. It maps to EP plus 1 R H Q T direct sum E P. I think it's T plus 1. Yeah, minus 1 P plus 1. It should be yes. Yeah, B R plus 1. Q plus 1. T minus 1. Yeah, so it can be decomposed into two parts. This part is the Euro E prime, this differential. The other part actually is the so-called wedge product with this Cordova-Spencer map. So here you see somehow we have to Cordova-Spencer multiplication. We have really want to incorporate this variational combine structure into the picture. So that's why this is yeah, this is special to this setting, but it's somehow on the other hand it's a well developed theory, which is studied by many people. Like sometimes it's also related to this so-called Higgs band, because this theta it's a Higgs field. It's related to this it's Cordova-Spencer class. Right. So it's in this special setting, then we have this D prime, D double prime lemma, which allows us to again be able to find this time, and then we can modify Q by chi again. So then you can achieve that D Q minus chi is in F3, which means that now you can write this as something like something like this. Actually, yeah. So then this becomes a just this thing. Again, so it's 2 1 plus 1 2. So you may have also so, and the complex conjugate. But then I guess you can show that this actually is a constant. It's a constant because on each fiber it's closed, so it must be constant. So this means that this actually, when you replace Q by Q minus chi, it's a pullback of some form on the, sorry, dq is pullback of some form on the base. Yeah. For some 2, 1 on the base, plus 1, 2 on the base. But then this is exact, right? So this is exact. So you can again write this as d of yeah, you can write this as d of chi b or something. So in the end, you can achieve that dq minus chi b is 0, right? So then that's what we want, right? So we get close the 1-1 form on the total space, such that yeah, as you point out, the restriction on each fiber doesn't change. It's the same as before. It's scalar. And then we can just pull back a kinematric on the base, and this becomes scalar. Okay. Right. So this finishes the construction. Right? So you see that the construction is not as easy as before. So basically, we need to modify the form instead of just finding a potential function to modify. So this is one thing I find interesting, because you see, so I guess in the study of this question, this Hermitian symmetric structure, people have been trying to modify, for example, a symplectic form to cancel its 2-0 or 0-2 part. But of course, that's very difficult, because you have to deal with the equations for forms. But here it's in this special setting, it turns out we can do this. Of course, we start with the 1-1 form, and we gradually cancel out the dq, right? So the dq, we in general have the 2-1 plus 1-2, right? So we gradually cancel these dq terms. So, and we do this by using this d development repeatedly, but you see that there are some points we have to use some extra structure for this Gauss-Money connection. I mean the cohomology, the Hodge theory for this Gauss-Money connection. So that's the new ingredient in this construction. So in the case of Blanchard, when he considers such example question, in his case this V1 is just because it's isotrivial, and when the monodromy group acts trivially, then this is just R, right? So this is just the usual not R, sorry. It's just a trivial local system. So there's no monodromy action. Then you can just use the ordinary DD by lemma. But here we have a non-trivial monodromy action in general. Yeah. So then we have to use the DD by lemma for this D. Yeah. So that requires more advanced result. Yeah, I think that's yeah, the roughly the proof. I think probably I just stop here. Yeah, thank you very much.
Okay, yeah, thanks, Chi. That's great. So let's give him a little applause. Any more questions? I guess I'm kind of curious if I don't know if do any of the analytic details like simplify in specifically the Hermitian symplectic case, like with this assumption around?
Uh, Actually, in the formation semantic setting, I just um, apply this construction directly because that's probably a different type of question.
Yeah, I understand. Yeah, I understand that the proof is just a corollary. I'm just sort of curious if maybe the analysis it might be easier
Right.
with that assumption
So
around forever.
I don't know because in the formation semantic problem, even in the homomorphic subversion situation, the only thing um, because I guess if you do this construction, you just get closed to form there. That's exactly the assumption for this theorem. Yeah. So of course, probably you have a I don't know, maybe this assumption. Um, yeah, but that assumption somehow is used to prove this condition. Yeah. So as for whether it simplifies the construction, I don't see how it will simplify. Actually, because I have to also assume that you see that in this case, I cannot I still cannot show this condition 1A completely. So actually, I cannot use this directly. So
Sure.
you have
But
to
like these kind of spectral sequence arguments and this like Deligne cohomology and stuff, none of that is any better if you assume it's holomorphic symplectic to begin with.
so you still have these results. The problem, I guess, is that right. So somehow to apply this Deligne's result, you need to have this local system is so-called polarized, which means that you have a pairing because in the Euro, if in the absolute case, for example, if you have a Kähler manifold, then you have a polarization, which means that you have a binary pairing on the cohomology class, which satisfies the so-called Riemann-Porch binary relation. So of course, if you restrict this, if you know the restriction to each fiber is Kähler, then on each fiber you have this polarization. But if you just know it's a Hermitian symplectic, then when you restrict a Hermitian symplectic structure on each fiber, it's just a symplectic form. Of course, you know that let's say the 1-1 part. I guess you take the cohomology class. It's a cohomology class, and then you take the 1-1 part. You can show that this is Kähler. This actually appears in paper of Li and Zhang. They use this Lemma points criterion to show that this is always Kähler. So in principle, you have the polarization on this on each fiber VB, right? V, right? So this is like the H. Anyway, so you have this XD. You have the polarization. The problem is that you want to put this polarization together, but then that requires this to be. So this is in H1 XBR, right? Which is contained in H2 XBR. So you want to. So in Deligne's theory, you don't just need a polarization on one fiber. You need a family of polarization. Actually, that's always true for this theory. In the theory of variation of polarized Hodge structures, you want the polarization to be flat. Yeah, need the polarization this by binary pairing to be horizontal with respect to this Gauss-Money connection. That's exactly the first condition, like this.
Okay.
But the problem is that I don't know whether this is always when you extract the one part, whether it's still horizontal with respect to the Gauss-Money connection. If you just take the Q, this cohomology class, this is the flat because you have a global class when you restrict to each fiber, then that gives you a horizontal section. So this is always H0 B R I star. So this is always horizontal, but after extract the one part, I don't know whether this is horizontal. This horizontal, you see, so actually probably you can see more clearly why. Let's say look at the double point part. Then, as we said, there are two parts. Right. So somehow if in the isotrivial case this theta would vanish because the combine structure does not vanish. In that case, actually you can show that when you extract the one part, it's still horizontal. But if you have this non-zero theta, then you see this one part and the 2 0 part would mix together, right? Because the 2 0 and the Q 1 and then that would give you some like a theta bar, theta 2 0 plus theta, something like this. Yeah. So right. So anyway, so what I want to say is that when extract this one part, I cannot conclude this is a horizontal bilinear form with respect to this Gauss-Money connection. That prevents me to apply Stirling's result. Yeah. So that's why I have to add this assumption as like a isotrivial assumption to make sure that this when I extract the one part, I still get
Okay. Yeah.
flat pairing. Yeah.
I see. Yeah. Thank you.
Okay.
Can you?
Others? Oh, please.
Yeah. Is there anything you can say when you have like some sort of mild singularities for the vibration?
Right. So that's another question. I don't have a result now yet. Although I think it should be possible to extend to the case. For example, I think the interesting situations once you allow this fiber to have nodal singularity. For example, in the case of like pencil, like Lefschetz pencil case. Yeah, because I forgot to mention that if you want to do these things in the symplectic setting, there's a result by Thurston, which give the criterion for the existence of symplectic structures on the total space of a fibration. And the condition is it's basically the same. It says that you have a cohomology class that is invariant under the monodromy action, but there he does not consider any compact structure, so there's no like a 1-1 type of condition. Yeah. So the Thurston also has a result for existence of symplectic structures, and his result has been generalized to the singular vibration setting by Gompf. So there's an existence result by Gompf which allows singularities. For example, the Lefschetz vibration case. Yeah.
Mm-hmm.
So I think there should be a corresponding result in the Kähler set. But then, for example, if one wants to construct Kähler metric, then have to be to use more information about the singular fibers. But on the other hand, the good news is that the Ling's theory actually has been extended to to that setting by Zucker. Yeah, long time ago. Yeah, so in principle there should be a way to do that, but I haven't thought of yeah, yeah, I haven't thought very carefully about that.
Okay, thank you.
Okay, any others?
May I ask?
Yeah.
I just put the video, sorry. Maybe a stupid question. As far as I understood, you assume that the base is scalar, right?
Base is scalar, yeah.
Yeah. Can you extend the result assuming that the base satisfies the DDC lemma?
What lemma? DD-bar lemma?
DD-bar lemma, yes, the DDC lemma.
No, but so if you want to find the Kähler structure on total space, then actually B is automatically Kähler. So the base is automatically there. So it's
impose scalar. If you impose scalar, when you impose X scalar.
Yeah. So it's a natural assumption. If you just assume B is DD-bar, then
No, I was wondering about the Hermitian symplectic structure on X.
what is symplectic structure?
Hermitian symplectic structure, which is weaker than Kähler on X.
Oh. For symplectic structure, as I said, the Thurston has this result. Yeah, I think in his case, as he assumed the base to be symplectic, I forget the. Yeah, probability base is also symplectic. Yeah.
Okay, I see. I see.
If you don't assume Kähler, then probably just get to the end, last step, because in the last step we need to use B to be Kähler to find this eta B, and then also you pull back some metric from the base.
Okay, I see. Okay, thank you very much. Thank you.
Okay.
Okay. Well, okay, yeah. Thanks, Chi. It was very interesting. Thank you.
Okay, thank you very much for your time. Okay.
Thank you.